Hello friends, welcome you all on your PD education. So friends, as you know that we are just providing you previous year questions with a brief explanation of GATE XE C paper, that is material science, engineering science के अंडर material science paper का mechanical part I am uploading and electrical part of material science will be uploaded by Kailash sir. Okay, I have already uploaded the GATE 2011 paper, so please visit that paper also. Now without wasting any time, let's start the paper. So here you can see the first question is, which of the following is not a Bravais lattice? So we have basically 14 Bravais lattice. Okay, so list of that is there. I will provide you that list also. And out of this list, which of the following is not Bravais lattice? Okay, so face center tetragonal is not Bravais lattice, but here you can see that these are the Bravais lattice. Simple cubic is there, BCC cubic is there, face center cubic is there, simple tetragonal is there, body center tetragonal is there, simple orthorhombic, body center orthorhombic, base center orthorhombic, face center orthorhombic is there, rhombohedral, hexagonal, simple monoclinic is there, base center monoclinic is there, and triclinic is there. Okay, so all these are, I can say, Bravais lattice. Okay, and out of this, face center tetragonal is not a Bravais lattice, I can say. Okay, so you have to just remember that there is no concept behind that. Now, as a Schottky defect is an ionic crystal, in an ionic crystal is a stoichiometric defect of cation, anion, cation and anion, and cation and anion interstitial. Okay, so यहाँ पे cation and anion vacancy है, interstitial है, यहाँ पे vacancy है, यहाँ पे vacancy है. So which of the following is correct? So here you can see option number C. So it is, I can say, here crystal. Okay, it is a crystal, I can say. Sorry. No, this is the basic definition. Okay, so there are different I can say defects are there. Schottky defect occur when a pair, here you can see a word pair is very important, pair of one anion and cation. Okay, so when anion and cation is missing from its from an ionic crystal. Okay, when ion and cation is missing, I can say. So if anion, that is basically positive and negative charge, both will miss, then whatever the charge initially is going to remain same after missing of that cation and anion. Okay, so it will maintain the electrical neutrality of the structure. Okay, the density of ionic crystal decrease due to the presence of these defect. Obviously that here there is no defect, I can say here there is a defect, here you can see. So as less number of atoms, and then we can say there is a lesser density, and it will occur, this type of defect occur in NaCl, sodium bromide and sodium chloride, I can say. Option number C is correct for this. Now, which of the following is best magnetostrictive principle? So direct questions are there. Magnetostrictive is that basically if you give electrical energy to any basically metal, then it will start vibrating, or I can say it will start contracting and expanding. So which of the following is best magnetostrictive principle? So directly you have to remember option number A. Okay, so here you can see magnetostrictive is a property of magnetic material that cause them to change their shape or dimension during the process of magnetization. Okay, so when the current is going to flow, they will going to magnetize, and after magnetization they will going to change their shape, I can say. Okay, so this basically is best example of magnetostrictive principles. Now again a database questions are there. Which material has lowest specific heat capacity at room temperature? So lowest specific heat capacity. Okay, so if you have directly, if you can directly remember the values, then you have to remember. Here you can see the values for water, for mercury, copper and silver. So option number B is correct for this, that is mercury is there. Now copper strain can be measured, micro strains can be measured by X-ray diffraction using peak. Okay, so area and intensity, position and area, broadening and intensity, positioning and broadening. Okay, so which of the following is basically used, I can say, by using the peaks method, that जिसमें peaks बनते हैं आपके पास, ये आप देख सकते हैं ऐसे peaks बना, then ऐसे करके कुछ एक और peak बना, ऐसे करके और एक peak, ऐसे different peaks बनते हैं. Okay, so it will show the intensity and it will show the angle, I can say. This is the graph that you draw. The relation is also there between these graph, between this theta and lambda by Bragg's law. So Correct answer for this is option number D. That is broadening, when you broad it and when you correctly position it. Okay, then you can measure the micro straining. Obviously, if there is a micro straining, then you need to broad it. Now, this is again a direct formula of this question, that is PB ratio. Okay, on pilling, Bedworth ratio is defined as the ratio of volume of oxide to the volume of metal, weight of oxide to the weight of metal. Then what is going to happen here? Suppose when a oxide layer is formed, okay, a oxide layer is formed on metal like this. Okay, so depending upon the thickness of oxide layer, the resistance to corrosion will occur if the thickness is going to increase. So as compared to the metal thickness, how much oxide thickness is there, that will basically compared, or I can say the weight of or volume, whatever the basically phenomena is, that will basically compared by using this PB ratio. So let me give you the answer, option number A, that is whatever the volume of oxide to the volume of metal. Okay, as the area is same, so we will take the thickness also. Okay, that thickness of this to thickness of this. So this is the formula. I am not going to in depth of this formula, just giving you the answer. Okay, now here you can see again, if you know the basically units of this, then you can match. Here you can see the properties are there and appropriate units. So directly let me give you the answer so that you can understand surface energy, fractal toughness, magnetic permissibility and thermal diffusivity. So thermal diffusivity is meter square per second. Fracture toughness is, I can say, Newton meter raised to power minus 3/2. Surface energy joule per meter square, and magnetic permeability Henry per meter. Okay, so some units are from electrical I can say topics, and some units are from mechanical topic. Again same basically same category of question. A characterization technique is there, and with the option in column number 2. Okay, so here you can see scanning, tunneling, microscopic scanning, electronic SEM, it is also called SEM in short. Transmission electron microscopy, atomic force microscopy. No vacuum is required. Back scattering electrons, photoelectron, atomically sharp tip, sub angstrom resolution. So which of the basically following is basically I can say the in which of the given quantities in column number 1 used in column number 2, I can say which of the, like no vacuum is required in which of the following method, that we have to match. So let me give you here answer, that in case of scanning, tunneling, microscopy, atomically sharp tip is required. Okay, and scanning electron microscopy, that is SEM, back scattered electrons are there used. Transmission electron microscopy, sub angstrom resolution is there. Atomic force microscopy, no vacuum is required, I can say. Okay, so if you know the theory of this topic, then you can answer. Obviously we have discussed also. Now here you can see the materials are there and their applications are there, like this titanium dibromide is there, boride is there. Okay, then molybdenum dislide is there, hydrophytite is there. So we have to match it with the following. So let's see the solution here. Here you can see the solution of this. Okay, so again the properties are same, then you have to answer. Now let's move to the next question. Now next question is basically related to your again properties and option, that is what is the meaning of that property. Okay, definition I can say. Here you can see property, and here is the with the option in column number 2, like toughness, resilience, creep, hardness, area under the stress strain curve, area under the elastic part of stress strain curve, total elongation at failure, time dependent. So time dependent property is creep, I can say. Okay, resistance to plastic deformation is, I can say, hardness. Okay, and resilience and toughness. So toughness is, I can say, total area. Okay, a total area under stress strain curve, and resilience is area up to elastic limit. So P ka 4 is there, so this may be or this may be. Resilience, that is Q ka 5 is there, so option number C is correct for this. Okay, so here you can see. Now this is a very important question, and I will give you a detailed explanation of this. Determine the mole fraction of vinyl chloride in a copolymer of vinyl chloride and vinyl acetate. Okay, so there is a polymer which contain vinyl chloride and vinyl acetate. Now what is the mole fraction, or I can say weight fraction or molecular weight fraction of vinyl chloride in this polymer, जिसमें vinyl chloride and vinyl acetate है, having a molecular weight of polymer is 10520 gram per mole and degree of polymerization is 160. Degree of polymerization, you know that weight of that divided by average weight, okay, average molecular weight. So here you can see given molecular weight of your copolymer, degree of polymerization is given, we can calculate the molecular weight of two components, that is vinyl chloride and vinyl acetate, that is 62.5 and 86 gram per mole. Now you know that there are two components only, so if I just add the fraction, suppose if one is present as 40%, then other must be 60% and sum must be equal to 1. So fraction of vinyl acetate and vinyl chloride I can say is equal to 1, or I can say vinyl vinyl acetate equal to 1 minus vinyl chloride. So I hope this is clear to you. Now you know that average molecular weight of the copolymer is, here you can see average polymer average weight, okay. So what is the whatever the molecular weight of vinyl chloride into the percentage of that vinyl chloride, molecular weight of vinyl acetate into percentage of that vinyl acetate I can say, okay. Now I can replace this quantity by this quantity, from there I will get equation number 2, and this is very important concept of making this equation. Now we know the formula of degree of polymerization is equal to molecular weight of polymer divided by molecular weight, average molecular weight I can say, okay. So from here I can calculate the average molecular weight, because molecular weight of copolymer is given to you 10520 and degree of polymerization 160. So from here you can calculate this. Now if you know the molecular weight, average molecular weight, okay, then by using this equation and basically by using these three values I can say, okay. So here you can see I can put the value, this value and this value is basically 65.75 I can put here like this, equal to the 62.5 that we have calculated here, and 80 for this 86 we have calculated here, okay. So from here I can calculate the fraction of vinyl chloride, that is 86%, okay. Very easy question but a tricky question. Now next question is your from phase diagram. So a plane 0.45% carbon steel is cooled slowly from 900 degrees Celsius just below the eutectoid temperature, okay. So this much carbon percentage is there and below eutectoid temperature 723 से आपने cool किया, तो this is the reaction. And during the cooling from this temperature to this pro-eutectoid alpha and gamma, find the volume of pro-eutectoid alpha just below 723 डिग्री सेल्सियस, ओके. तो आपको वो कैलकुलेट करना है कि pro-eutectoid alpha कितना बनेगा. So let me give you the solution. So volume percentage of pro-eutectoid ferrite or alpha I can say. So whatever what is actually given to you, okay. So you know that eutectoid point is going to occur at this, okay. Let me give you the diagram. Here you can see this is the diagram. So this is eutectoid point at 0.8% of carbon, 0.80% or 8, and this point is given to you 0.45, and this is the point, or I can say maximum solubility of carbon in alpha. This is alpha region I can say. So I can apply the lever rule in this. So if I want to calculate the alpha, as this is alpha region, I can say if I make the line, this point is 0.45, this point is 0.02, and this point is showing you 0.80. This region is alpha dominating region, and this is I can say iron carbide dominating region, okay. Now what is basically we have to calculate it, we have to calculate pro-eutectoid alpha. Now alpha rich region is this, so we have to take the opposite region of this, that is the difference of this 0.80 minus 0.45 divided by the total, that is 0.80 minus 0.02 into 100, we can calculate the percentage. So 44.9% of pro-eutectoid alpha is there. Now find the volume percentage of perlite for just below this for 0.458 of carbon. Okay, now we have to calculate the volume percentage of perlite in this. Okay, so again we can calculate the perlite also. Similarly here you can see that volume percentage of perlite at this. Okay, so if you just make this again, if you make this diagram again, okay, now you know that this is given to you. Okay, these are the 3 points given to you. Let me draw these 3 points here: 0.02 and 0.45 and 0.80. I can say in the last, I can say I have mentioned here, this is basically actually perlite region, I can say. Okay, because at 0.80 perlite is going to form, so perlite is going to form here like this, and here alpha rich region. So we have to calculate the percentage of perlite, so we have to take the opposite of this: 0.45 minus 0.02 divided by total is going to remain same, so 55.1%. Now this question is, I can say, from strength of material. A load is applied on the axial steel bar, so a steel bar is there, 20 kilonewton like this, and area of cross section, I can say 8 centimeter square, and a length of 1 meter is there. The Young's modulus of steel, I can say 200 gigapascal, and aluminium is there also given 70. The Poisson ratio is this 0.3. When the same load is applied to aluminium bar, it is found that found to be given same elastic strain is same as the steel. Calculate the cross section area of that bar. Okay, so strain is, I can say, same. So strain means change in length divided by original length is going to remain same for steel. Okay, so what is the cross section area? Okay, when same load is applied, so there is a formula that change in length is equal to PL by AE. Okay, so what is given? Strain is same, so delta L by L divided by P equal to 1 by AE. Can I write it like this? Yes, we can write it like this, because delta L by L, strain and P, it is same, so it is constant. So 1 by A1 E1 is equal to 1 by A2 E2. It is given to us. So E1 is given to us this 200, E2 is given to us 70, A1 is given to us 8. So we have to calculate this. So I can write A2, we have to calculate E2 70 and then 200, then into, I can say, 8. Okay, from here we can calculate like this. I can cut it, and then 8 into 2 16, 0 divided by 7. So we have to calculate A2 from this. So whatever the answer we are getting from this for A2, okay, so you can get A2 from here 22.86. okay, 22.86. so I hope as 7, if I just multiply it with like this, okay, let me divide it also, if you can confirm it like this, 14 into 2 divided by 2 0, and 7 2s again 14, then 6, then point is there, then 6 is there. Okay, so I can just put 56 here. Okay, so I can put 56, so I can say yes, 86. Yes, this is the answer, option number D. Now for same question, calculate the final area of steel bar after the deformation under the applied load. What is the final area of steel bar after the deformation? That we have to calculate. So Poisson ratio is given to us. Okay, Poisson ratio is given to us. We have to calculate the final area of steel bar after the deformation. For this we have to calculate the true stress and true strain, that is formula. So for true strain, the true strain is log of original area divided by final area. So strain is basically we can calculate by change in length divided by original length. Okay, we can simply calculate that also. Okay, so change in length divided by original length equal to P by AE. So load is given to us, area is given to us, E is given to us for steel. From there we can calculate the strain, and if I put strain here, original area here, we can calculate final area as 7.99 centimeter square. Now Calculate chromium has BCC structure with atomic diameter of this. Atomic diameter is given. Calculate the lattice parameter of chromium assuming tight atomic bonding. So it is very simple question. We have to calculate lattice parameter. So here you can see for chromium, okay, the structure is BCC, and for BCC the relation for atomic radius and I can say your this lattice parameter A is this. So if diameter is given, you can calculate radius, and from radius you can calculate this parameter also. Now again same question, but in this case find the first diffraction peak position to theta for chromium K alpha radiation with the wavelength of this. Wavelength is given to you. We have to find the first peak of first position, like this. If this is the intensity, if this is the theta, there is a first peak, after that second peak, like this. So at what theta this peak is observed, we have to use this. Okay, for this there is a direct formula by using Bragg's law. Okay, 2d sine theta equal to lambda, and d from basically relation of a divided by h square k square l square. From that you can calculate. Okay, now BCC, for BCC first diffraction peak will be at 110. You have to remember this. After putting h equal to 1, k equal to 1, l equal to 1, a basically that you have calculated in previous question, I can say 2.880. okay, 2.880, and 2 is there, theta and lambda is given to you. You can calculate theta, and then you have to multiply theta by 2, that is equal to 22.216 into 2, 44.43 degree. Okay, so friends, these are the questions from GATE 2012 in XEC material science. If you have any doubt in then you please mention in the comment section. Okay, thank you very much friends, and we will meet in the next video.